and welcome to all. This is the third lecture of spectroscopy techniques and application, and it is the basically in continuation of UV visible spectroscopy. So, in this lecture I will cover the shifting of absorption and intensity maxima in UV visible spectroscopy and then Beers-Lambert's law and its derivation. The references are same. Organic spectroscopy principles and chemical applications by Y.R. Sharma, engineering chemistry by Jan and Shashi Chawla, and one another book for practice for numerical I preferred principles and practice for analytical chemistry, F.W. Weifield and Cayley. Now, so shifting before this transition of electron, bonding electron to anti-bonding electron, we have already discussed in previous lecture. So, here I will discuss the absorption and intensity shifting. This is the absorption maxima, and what is the absorption maxima? If we draw of absorbance at various lambda, so at which lambda the maximum absorption occur, it is called lambda max. So, due to presence of conjugation or some foreign group, there may be shifting of this absorption maxima. It may be towards right side, towards left side, towards upward or downward. So, we will find what is the reason of this shifting. So, first is Pathochromic shift, and this shift is also known as red shift, that is towards longer wavelength. And how we find this is a longer wavelength? Remember Woodward. So, if we move from bluish or violet color towards red, then this is called red shift or towards longer wavelength, because the wavelength of violet color is about in range of 4000 angstrom, and while it is of 7800 angstrom. So, it means violet to red color, that is towards longer wavelength. So, first if shifting is shifting of absorption maxima towards longer wavelength. This is called pathochromic shift or red shift, and this is due to presence of oxochrome or by change the solvent, or we can say polarity of solvent. And one another reason is if we increase the conjugation, it means the shifting of maxima, it will goes towards higher side. And for remember we can find, even we will do the practice in last slide. Suppose this CH3 CH single bond CH2 CH3, and one another example is CH2 double bond CH single bond CH double bond CH2. In second case there is a conjugation, while in first case no conjugation. Conjugation means more easier means energy will be less, energy will be less means its lambda will be high. So, remember this point, more conjugation means shifting towards higher value of lambda. Example is for carbonyl group means CO. So, in carbonyl group, if the polarity of solvent is decreased, it means the N to pi star transition, it will experience red shift. Red shift means it will shift towards longer side. Now, second shifting is blue shift. Blue shift means hypochromic shift. Blue means towards violet side, that is shorter wavelength. So, if the absorption maxima, that is lambda max of compound shift towards shorter wavelength, it is known as blue shift or hypochromic shift. Now, just remember reverse thing, due to removal of conjugation, maybe removal of oxochrome, maybe change the polarity of solvent, it may cause this type of shifting. Let us take one example. Suppose in case of aniline. Aniline is the benzene ring with NH2 and nitrogen has one lone pair of electron. This electron is available for conjugation in a benzene ring. It means there is a chances of conjugation. it shows lambda max at 280 millimicron or nanometer. But in acidic solution, the lone pair it get involved with bonding with H. That is no availability of lone pair of electron. That is there is no conjugation within a ring. It means its lambda max value decreases, and which is about 203 nanometer. So, I think it is clear. In benzene ring, electron available for conjugation, so it shows higher value of lambda max. Now, third shifting is hyperchromic shift. So, it is not towards right side or left side, it is toward upward. So, if the absorption intensity increases, because on y axis we can take intensity also, and intensity roughly you can say about epsilon. We will discuss this later. So, if the height of absorption maxima it get increased, this is called hyperchromic shift, and generally it is due to introduction of oxochrome. So, if we introduce some group which may act as a oxochrome, the intensity of absorption maxima it get increased. For example, in case of pyridine and 2-methyl pyridine, pyridine shows a band at lambda max 257 millimicron or nanometer, and its epsilon value, which is directly related to the intensity, it is about 2750. But when methyl group get introduced in this pyridine ring, its epsilon value it get increased, that is intensity increase. So, in this case CH3 it increases the intensity of this absorption maxima, that is it leads towards hyperchromic effect. Now, next is hypochromic shift. Hypo means downward direction, that is height of absorption maxima it get decrease. For example, there may be some group which may causes the hypochromic shift. For example, generally we prefer biphenyl. So, in biphenyl its epsilon value it shows a band at epsilon value 19,000, but in case of 2-methyl biphenyl or naphthalene its epsilon value decrease. It means this CH3 group at this ring it cause or it lower the intensity, that is hypochromic shift. So, I think 4 shift are clear: bathochromic shift, hypsochromic shift, hyperchromic shift and hypochromic shift. Towards longer wavelength, towards shorter wavelength, intensity increase, intensity decrease. Generally intensity increase by introduction of oxochrome, and hypochromic shift there are some group which decrease the intensity. So, this is the summary of this shifting. Now, effect of polar and non-polar solvent on N to pi star transition. Solvent, generally we prefer the solvent which does not react or which does not show absorption band in particular region. 95% ethanol is most commonly used solvent, but commercially ethanol is not used, because in this benzene is added and which shows a band in this region. For non-polar compound, its absorption maxima does not shift for any value or we can say in polar solvent as well as in non-polar solvent. But in case of polar compound, generally for pi to pi star transition, when we prefer polar solvent, its lambda max value get increased. It means the energy gap between the pi and pi star molecular orbital it get decreased. This redshift is caused when excited state is more polar as compared to ground state. The reason behind this, in ground state and excited state, since excited state is comparatively more polar, so this polar solvent it stabilizes the excited state as compared to ground state. So, overall the decrease in the energy gap between the excited and ground state, and that is why lambda max value increases. For example, acetone with water. But in case of non-polar solvent, the lambda max value it is decreased. It means blue shift occur, because for non-polar solvent the ground state is more polar than excited state, and the this solvent, it stabilizes the ground state as compared to excited state, and that's why the overall energy gap it get increased. So the lambda max value decrease. So the summary is, for polar and non-polar, for pi to pi star transition, when we increase the polarity of solvent, its lambda max value get increased, and for n to pi star or n to sigma star, the lambda max value get decreased. Now, next is most important rule, Beer's-Lambert's law, and this is the basically combining form of Lambert's law and Beer's law. First we take Beer's law. This law states, when monochromatic light passes through a transparent medium, the rate of decrease of intensity with thickness of medium is proportional to intensity of the light. It's simple. The rate means d by d. Decrease means minus d. The rate of decrease of intensity with thickness, let the path length of thickness is L, is directly proportional to intensity of light, that is I. That is minus di by dl is directly proportional to I. And let's we take with equal value. So minus di by dl is equal to, let's any constant, suppose A, and this is I. So minus di by I is equal to any constant, and this is the path length I. Let the initial intensity of light is I naught, and after passing through medium its intensity is I. Initially the length is 0, and after passing the medium its length, it covers the length L. Suppose this is, and we pass the light, this intensity I naught, and after passing through medium its intensity become I. So when we solve this, we will get I is equal to I naught e raised to the power minus a L, where I and I naught is the intensity of light after passing the medium and initial respectively, A is the constant and L is the thickness of medium, that is path length. Generally Beer's-Lambert law we calculate at 10th value of log, that is with the log. So we can write I is equal to I naught 10 to the power minus, let any constant, suppose k, into L, where A and L both are constant, and k is equal to A upon 2.303. So this is the first equation of as per Lambert's law. Now Beer's law. Beer's law basically give the effect of concentration of colored constituent in solution on the light transmission or absorption, and Beer's law is also same, but in this the statement is, when the monochromatic light passes through a transparent medium, the rate of decrease of intensity, that is minus di, with thickness, that is dl, is directly proportional to intensity as well as concentration of the solution, I as well as C. And when we solve this, we get I is equal to I naught 10 to the power minus, let here we take k and here k dash, C and L. This. So the basic difference C. So Beer's also studied the effect with the length as well as with concentration. Now by mixing both law, so when we mix both law, it becomes I is equal to I naught 10 to the power minus constant, combined constant, and suppose combined constant is epsilon Cl, where epsilon is the extinction coefficient. So, we can write here I is equal to I naught 10 to the power minus epsilon after solve this. So, epsilon 1 by 2.303 k, and which become this epsilon. So, here this is 1 by 2.303 and overall value of k. So, I upon I naught is equal to 10 to the power minus epsilon Cl. Now, to delete this minus, so we can write log of, by taking log on both sides we can say, so log of I upon I naught is equal to minus epsilon Cl, and we know that if we reverse this, so minus value get here. So, log of I naught upon I, it will become epsilon Cl, and this log I naught upon I, this is called absorbance. So, what is the basic form of Beer's-Lambert law? Beer's-Lambert's law is absorbance, that is log of I naught upon I is equal to epsilon. Epsilon is the molar absorption coefficient or absorptivity into concentration. Concentration may be in gram per liter or mole per liter. If we take in gram per liter, this is called absorptivity. If we take in mole per liter, then it is called molar absorptivity into L. L is the path length or thickness of the medium. So, A, and with A we can also find transmittance, how much value of light get transmitted, and this transmittance is equal to I upon I naught. So, if we find a relation between A and T, we can easily say that A is equal to log of I naught upon I, so which is log of 1 upon T, that is A is equal to minus log T, this. And how this transmittance value get occur? In instrumentation, we suppose we take a double beam spectrophotometer. So, split in light into two parts, and at one side we pass this light, and let the initial intensity of light is I naught. We pass this light through a water or a solution or solvent which does not absorb any part. So, the value which get transmit, its intensity will also be I naught. But here suppose we take a sample, and we know that after passing through the sample, few part of this it get absorbed, let the after passing this medium, let intensity is I. So, the factor which relate I with I naught, this is called transmittance, and with the transmittance absorbance can also be calculated. Okay. So, Beer's-Lambert law is simply A is equal to epsilon Cl. It means the if a monochromatic light is passes through a medium, homogeneous medium, then its absorbance, it will be directly proportional to its concentration if the thickness taken unity, and or we can say absorbance is directly proportional to its absorption coefficient if the concentration is taken 1 or unity or length is also 1. Or we can say if the length it get concentration and length are in inverse proportional, then its absorbance remains constant. Suppose we say solution, its concentration is 2 and the thickness of medium is 1 centimeter, but when the concentration decrease 1, so what will be the L? So, we can basically correlate with this. Now, so there are two terms in big font. First is transmittance, which is I upon I naught. Don't be confused in I naught or I or this. So, transmittance after absorption divided by initial, and absorbance is log of I naught upon I. And here this is the simple representation. Here we take absorbing sample of concentration C, initial intensity I naught, and after passing I, and path length is here n. This is the simple presentation of curve, or we can say verification of Beer-Lambert's law. A is equal to epsilon C L. It means for a fixed value of L and epsilon, A and C has a linear relationship. It means for a same spectrophotometer, if we draw a plot in between absorbance and concentration, we get a straight line passing through a origin. But there may be some deviation after the one value. But instead of this absorbance, if we draw a plot between T and C, that is transmittance and concentration, we get this type of plot. If we draw a plot in between log T and C, we get this type of plot. But this is the final, or we use this concept in a practical or in determination of concentration of unknown solution. If we know the absorbance of solution and we know the various concentration, but we can find the unknown concentration because we can relate with the absorbance with this concentration. Now, there are two numerical based on this Beer-Lambert law. First numerical, it is a very simple, and this is in Shashi Chawla, you can see. A compound having concentration 10 to the power minus 3 gram per liter. The resultant absorbance value is 0.20 at lambda max 510 nanometer using 1 centimeter cell. So, A is absorbance is simple given, which is 0.20, L is 1 centimeter, C is 10 to the power minus 3 gram per liter, and we had to find absorbativity. Absorbativity means epsilon, and molar absorbativity is epsilon m. And what is the basic difference in molar and simple? Concentration in gram per liter, its value give epsilon, and when we take concentration in mole per liter, and we know that mole is equal to weight upon molecular weight. So, 10 to the power minus 3, its molecular weight should be given, which is 400. So, upon 400, it is in mole per liter. So, when we use concentration this value, we get epsilon m, and when we use the value of concentration 10 to the power minus 3, we get epsilon. Now, find this. We know that as per Beer-Lambert law, A is equal to epsilon CL. So, epsilon will be equal to A upon CL. A is 0.20, C is 10 to the power minus 3, L is 1, and what will be the unit? The unit will be 1 upon gram per liter centimeter. So, we will get liter gram inverse centimeter inverse. So, what will be the value? The value will be 200. Now, epsilon m, the epsilon m will be A remains same, that is 0.20, but now C will be in mole per liter, that is 10 to the power minus 3 into 400 upon 400 into 1, and what will be the unit? The unit will be liter mole inverse centimeter inverse, and which is 8 into 10 to the power 4, not minus 4, it is 4 liter mole inverse centimeter. Clear? Now, second, calculate the absorbance if the percentage transmittance is 80%. T 80%. T is equal to I upon I naught, and which is 80%. So 80 upon 100. Now A is log of I naught upon I. It means log of 100 upon 80. And when we solve this, we get the value 0.097. I think it is clear. So now next is limitation of Beer's-Lambert's law. The first limitation is monochromatic light should be used. Second limitation, dissociation of molecule. This can be explained by the fact that dichromate ion possess their lambda max at 450 nanometer, which is orange in color, but upon dilution it will dissociate into chromate ion, and now its max lambda max it will be, it become 410, which is yellow in color. So we can say on dilution it get deviate. This law is not valid in case of absorbing material is coagulated with a small number of large unit. Third, this law, it shows deviation if the absorbing material at required wavelength it possesses some impurities like benzene, commercially ethanol which have benzene. So if their type of situation, so this law it may deviate because of absorption maxima shown by benzene. At higher concentration it deviates, we have already discussed in this part, and this law is not applicable in case of suspension. So three main points. First, it is generally used for dilute solution for monochromatic light, and temperature variation should not be too much. Now application of UV visible spectroscopy. The main or first application is, this is useful for determination of conjugation or differentiate between conjugation and non-conjugation. So first simply we can write used in qualitative and quantitative analysis. It is used for characterizing aromatic compound and conjugated olefins, that is, it is used to find extent of conjugation. For example, in this, for example, in all these cases, the first case is, first we have to find out which will show higher value of lambda on UV absorption. First this CH2 double bond CH, single bond CH, double bond CH, this and this case. Here we see that there is a conjugation. Conjugation means double bond, single bond, double bond, single bond. But in this case we see that single, double, single, but there is no double. So in first compound there is a more conjugation, and remember this line, more conjugation leads to higher value of lambda max. It means this compound will show higher value of lambda max. It means we can also find the extent of conjugation. Second, it can be used to find the molar concentration of solute under study by using which formula, which law? Beer's-Lambert's law. We can find C, and when we know the C, we can find also molecular weight of compound. So determination of molecular weight. Detection of impurities, because if impurity is present, it will show a lambda max value. Detection of isomers. If isomers, and in which in those isomers where is the more conjugation, we can easily find or detect, and that is why it is very useful to find the structure of vitamins. It is also used the study of kinetics of chemical reaction, because we can find the for particular concentration higher for which concentration it shows higher rate or high speed. Now, there is a one we are taking a little give a small idea of Woodward Fischer rule, and which is not in syllabus, but we should know. This Woodward Fischer rule, it is used to find the value of observed lambda max, and this is basically derived given by Woodward in 1914, and which correlate with molecular weight structure with lambda max. But in 1959, Fischer modified the rule with more experimental data, and this modified rule is known as Woodward Fischer rule. And what is the rule? This is used to correlate lambda max of given structure by relating position and degree of substitution of chromophores. And what is the formula? The lambda max is equal to the base value plus substituents contribution plus other contribution. Let us take an example. This is the simple value, parent value of conjugated dye in heteroannular. Heteroannular means conjugation or double bond present in same ring, in different ring, sorry, and homo in same ring, like this situation, like this. This is hetero, and this is like homo, okay. And these are the substituents or increments. Now, let the question is, find the lambda max value of this. This is simple butadiene. It means conjugated diene, acyclic conjugated diene. So, its lambda max value is given, and which is approximately 215 to 217, and we prefer 270. But suppose here 3 methyl groups are attached like this, 1, and suppose 2, and suppose here 3. Suppose we want to calculate lambda max of this compound. So, here the calculated lambda max, it will be first lambda max value of parent, and parent molecule is butadiene, this, and its value is 217 millimicron. Now, there are 3 methyl group, and each alkyl group it contribute of 5 nanometer or millimicron, we can write it millimicron nanometer. So, there are 3 methyl group. So, 3 into 5, which is 15. So, the answer will be 232 millimicron. So, with this just idea, with the help of Woodward Fischer rule, we can find the observed value of lambda max by examining the structure of parent molecule and its substituent or oxochromes. Clear? So, I am finish this lecture here, and in next lecture I will discuss the IR spectroscopy.